Hi, good day. I'm Jason P. Lola. I'm a registered electrical engineer and a registered master electrician. I'm also certified safety officer 2 with a 40-hour course training. I teach electrical engineering subject for almost 4 years as assistant professor 1. And I'm handling competency appraisal course for 5th year EE students in preparation for their board exams. At the same time, I'm practicing in the field as an on-call site engineer and designing electrical system for private individuals. My specialty in teaching focuses on electrical system such as illumination, power plant, distribution, and I'm also considering construction methods. I engage some public speaking invitations regarding on teaching the know-hows and methods of electromagnetism to some senior high school teachers. As a teacher, I usually make lessons with the guide of core syllabus depending on student level and needs. So I encourage students to have enough opportunity to make some noise and building up their trust in talking and also questioning. At the same time, I can get to correct them immediately, and I make sure that they repeat their corrections, since practice is essential in learning effectively. Now, I also believe that teaching is listening and learning is talking. So I mean, having to find someone whom you can practice with. Now, let's get started. Our lecture for today is all about AC machines and specifically synchronous motors. Now, our objective for today's lecture is to understand, recognize, and deriving and have a working knowledge of performance and characteristics of synchronous motors. By the end of this lesson, you, my students, are expected to summarize the definitions and principles of this motor. You can explain now the theory, construction and calculations, and its applications. And you can now apply the electric circuit principles to solve various configurations, just like delta and Y configurations. Now, if an electromagnet is present in these rotating magnetic fields, as you can see in this animation, the electromagnet is magnetically locked with this rotating magnetic field, and it rotates with the same speed of rotating field. Now, the rotating field is the rotor. The rotating magnetic field is at the stator side. This is where the term synchronous motor comes from. So as the speed of the rotor of the motor is the same as the rotating magnetic field. Now that statement came up with a formula. Now it is a fixed speed motor because it has only one speed, which is synchronous speed. Now the synchronous speed is synchronized with supply frequency. The synchronous speed is given by this formula. Now we have 120 F over P. So this 120 represents your 120 degrees, the angle between conductors. Now the equivalent circuit per phase. In solving synchronous motor, we analyze it by per phase. Now we are going to pick on a single phase equivalent circuit. If you'll notice, it looks almost the same as the synchronous generator diagram, except it is backward. Synchronous motors and synchronous generators, they are more or less the same thing. They just operate in reverse. So that is the basic. So let us start from left to right. So this time around, we have an AC power source. Yes, this. And since this is a single phase equivalent circuit, we're only depicting one phase. This is going to be our line to neutral voltages. So literally where we put power on our stator is instead of producing power, this way we are now going to put power on our stator, creating a magnetic field between this in the stator that's going to spin the rotor. Now, the simplified circuit is conducive to obtain the basic performance characteristics of the machine, sometimes in the under steady state conditions. So these parameters include voltages, currents, power factor, and load angle. Now we have two representations of the synchronous motor by this formula. Now we came up with this formula through using of the Ohm's law basics. Now where EP represents your back EMF per phase, VP, supply voltage per phase, let's go back to the EP. EP represents the induced EMF. IP is the motor current, RA is the armature resistance, XS represents the synchronous reactance, and the two sign conventions in using this formula. We will use plus if it is operating leading power factor and minus for operating lagging power factor. Now the second one, you can solve it through phasor diagram equivalent. Now I have two phasor diagrams here, represents the over excitation and the under excitation. Those two keywords will be more important when representing the leading power factor and lagging power factor. And we came up with this formula in complex format. Now that is EP with the angle of delta plus minus equals the VP angle 0 minus IP that represents the complex format of your motor current, and the RA plus JXS as your impedance. Now, this delta represents the torque angle between your induced EMF and your supply voltage. The same still, our theta represents positive, it is leading, and negative for lagging. Now, before we proceed on the applications of synchronous motors, now we will study the effect of increased load in the synchronous motors under conditions. We have two. With normal excitations, we assume that the back EMF is equal to the supply voltage. With under excitation, your back EMF is less than the voltage, your supply voltage. And with over excitation, we have back EMF is greater than voltage, supply voltage. Okay, those are the important terms that we consider in solving synchronous motors. Now, before we proceed to some one problem solving example, the application of synchronous motor is for power factor correction. This is more important. This is the very important aspects of synchronous motor for our electrical system. It is used for constant speed applications because it operates less than 500 RPM, and it is preferably used for compressor, rolling mills, then for voltage regulation. Now we have a problem solving. Okay, let's try this. A three-phase Y-connected synchronous motor with a line-to-line voltage of 440 volts and a synchronous speed of 900 RPM operates with a power of 9 kilowatts and a lagging power factor of 0.8. So the synchronous reactance per phase is 10 ohms. So determine the induced EMF.
The problem states that it has three-phase Y-connected synchronous motor. Then the V line, 440 volts. The synchronous speed, 900 RPM. Power is 9 kilowatts, which is also 9,000 watts. The power factor operates at 0.8 lagging. Then the synchronous reactance is 10 ohms. We must find or determine the induced EMF, which is EP. That is the induced EMF. Now, that's all. Before to use the formula, let's convert it into equivalent circuit per phase. Okay, now we have this, which is our voltage source, synchronous and armature resistance. This is RA and XS. That's what we call the impedance. Okay, stator current. And now this is our EP, or the back EMF. Now, we will now use the formula in complex format, which is the back EMF or the induced EMF plus minus delta. That stands as your torque angle. Torque angle is the angle between the back EMF and the voltage source. So let's back. We have VP, angle 0 minus IP plus theta, then the impedance. So as you can see, in the problem, armature resistance is neglected. Take note, in Y configuration, IL is equal to IP. V line is square root of 3 V phase. Now, let's solve. Or to find the I phase, we have IL equals the power over square root of 3 VL, then the power factor. So let's provide all the values. Square root of 3, 440 volts, times 0.8. Now, I line becomes 14.76 ampere, and which is also your I phase. Now, to get the value of theta, which we have the power factor equals cosine theta. Now, theta is cosine negative 1, 0.8. Now, our value of theta becomes 36.87, and which is lag. And now we will use minus sign for our operation. Since we have V line equals square root of 3 V phase, now we will now provide these values into this formula. Now, EP 440 over square root of 3. Take note that is phase voltage, angle 0, minus 14.76, which is our I phase, the angle of minus 36.87, since the power factor is lagging, and we will now use minus sign, times. Take note, XS, or the synchronous reactance, is 10 ohms. So we will now convert it into complex format. So 10 angle 90 degrees. So we have 10 degrees. Now, compute it. We will now have a value of 203.281 angle negative 35.51 degrees. And now, our induced EMF, or the back EMF, is 203.281 volts. This will become our final answer. Take note, the angle here is our torque angle, and that provides 35.51 degrees.
Now this is your seat work. You can pass this tomorrow. Then the key points. So through this lecture, as load on the motor increases, armature current increases regardless of excitation. Remember that. For under and over excited motors, power factor tends to approach unity with increase in load. That is why the synchronous motor is highly usable for power factor corrections. Third is both with under and over excitation, change in power factor is greater than in armature current with increase in load. But with normal excitation, when load is increasing, change in armature current is greater than in power factor, which tends to become increasingly laggy. Okay, that's so much for today. Thank you and keep safe.